Hey y'all, it's good to see you guys. Today we are going to learn about something completely new, okay? So up until this point, everything that we've graphed, whether it be in this class or pretty much any other math class you've taken, you've graphed on what is known as the Cartesian coordinate plane. And that is a two-dimensional plane where you graph points along an x-axis and a y-axis. Another way that people refer to this plane is called the rectangular plane, and that's because you locate coordinates by essentially creating a rectangle with a length and a width, and then the corner, which is opposite of the one that's at the origin, is going to be where your point is. So for example, 2, 3 is 2 units to the right and 3 units up. There is another type of graphing system which we are going to look at in this unit, and it is called the polar system. So today we're just going to focus mainly on how to plot points and just kind of go through an intro as far as what the polar system is, how to use it, how to write equations with it, and so forth. So let's take a look at defining it and look at a few examples of how you would plot points in a polar system versus a rectangular system. So let's look at the differences here between the polar system and the Cartesian system. You are more familiar with the Cartesian coordinate system. And on the Cartesian coordinate system, you use x and y to name points. On the polar system, you are going to use different variables. You're going to use r and theta. To name points. Now, in the Cartesian rectangular system, the x represents typically your horizontal axis and the y represents the vertical axis. So if, for instance, you wanted to locate something that was 3 units to the right and 2 units up, you would write it as 3, 2. And to find that location, you would go 3 to the right, up 2, and then you would plot that point right about, well, that's a square. Let's try to use a circle here. There we go. Now we want to be able to locate points on the polar system as well, but it works a little differently. So instead of using x and y, we are going to use r and theta. So it might be a good idea to define what r and theta actually represent. So instead of, one thing that's similar is that whether you're using the polar system or the Cartesian system is you start at the origin. It's just that in the Cartesian system, this point, this 0, 0 is called the origin. This point is called the pole, and that's kind of why it's called the polar system. So this point right here, that is a little thick there. Let's try to make that a little smaller. So this point right here is called the pole. Okay, so you're still going to be starting from that center point, but we're just going to call it something different. Okay, so again, on the Cartesian system, it's called the origin, and in the polar system, it's called the pole. So if we want to find a point on this grid, instead of going to the right and going up, we are going to identify an angle measure and then use this r value to represent the distance from the pole. So let me write that down. Okay, so the r is going to be the distance from the pole. Okay, in other words, it's the origin. And theta is going to represent the angle in standard position. So just as a little reminder here, standard position is talking about having an angle measure whose initial side is along the x-axis and whose terminal side is just somewhere else. So as long as the vertex is at the origin and the initial side is right here, it's going to be in standard position. So the way that you are going to plot points in the polar system is It's a little backwards, I think, to be quite honest with you. In the Cartesian coordinate plane, you're finding the x first and then the y usually. But in the polar system, you're actually going to find theta first and then r. I'm not really sure why the convention has r come first, but in most cases, theta will be the input of your function and r will be the output, rather than in the Cartesian system where x is typically your input and y is typically your output. So just something that's a little bit different here. So as far as how to actually plot these points, and we'll go through some examples for sure, but the very first step you're going to do is, so let me write this out, to plot a point in polar form, you're going to first locate theta, okay? So you're going to figure out where is the terminal side of theta. If theta is pi over 3, it's going to be along this 60-degree angle measure. So first you find theta, and then you are going to move r units away from the pole in the direction of theta. So in other words, let's say we had a point that was 2 comma pi over 2. Well, theta being pi over 2 means we're going directly up. And then if r value is 2, you would just go up 1, 2, and put the point there. The reason why it's r is because we're really talking about the radius of a circle. Notice all of these circles are concentric, meaning they have the same center, and they should be equally spaced. So this is 1, 2, 3, 4, 5, 6, etc. So you would find your angle measure first, and then you would just go away from the pole that many units. So that's kind of the idea here as far as the differences between the polar system and the rectangular system, otherwise known as the Cartesian system. So let's try to plot some points that are given in polar form, and then we'll look at a few other things as well. So I've got essentially two problems here. I want to plot 1 comma 5 pi over 4 and 3 comma 3 pi. So it's a little harder to sketch these for sure. I would recommend just doing the best you can when you're trying to actually draw it out. But when we're trying to plot these points, we want to follow the directions that I gave on the previous slide here. And so let me go ahead and pull that over just so we don't have to keep going back there. Let's see here. Well, it doesn't like me copying this over. Let's see here. Here, I'll just do this. There we go. All right, I think we got it all fit on there now. So to plot a point, first we're going to locate theta. So if we want to plot 1 comma 5 pi over 4, then we are going to find 5 pi over 4 on our unit circle. And it looks like 5 pi over 4 is going to be right down here at 225 degrees. So in other words, we are going to start at the pole, and we are going to work our way out from the pole along that terminal side. Now it's 1 comma 5 pi over 4, so that means that I'm going to move just 1 unit out towards 5 pi over 4, and that means my point is going to be right here. So that's going to be A. I'll go ahead and label that. And let's do B, 3 comma 3 pi. So again, first find the theta. Okay, so 3 pi isn't explicitly labeled on here, but if you recall from, gosh, I think it was the first unit, it was like towards the beginning of the year where we looked at coterminal angles, we saw that 3 pi is really this in the same location as pi, and the reason for that is we go 1 pi, 2 pi, 3 pi takes us back over here. And so that point would be 3 units away from the pole, 1, 2, 3, and so our point will be right here. Oops, let's draw that. Let's draw that a little better. There we go. That's still a pretty ugly one, but it'll do. Now, one thing you might notice here is that 3 comma 3 pi is in the same location as 3 comma pi. Well, give me a pi? Nope. Let's see here. There we go. Nope, it didn't come up. Okay. We'll get there. What's happening? I got double pi. Okay, there we go. Sorry about that. So we got 3 comma pi. So 3 comma pi would be in the exact same spot. So you might be wondering, well, how do you know the difference between these two? And unfortunately, if there's just a point plotted on there, you really don't. There is no way to know exactly what it is. In fact, you could say it's either one. You could even say it's 3 comma 5 pi or 3 comma 7 pi. One huge difference that the polar system has versus the Cartesian system is that points are not unique. What I mean by that is in the Cartesian rectangular system, any given point can only be described with one combination of numbers. So for instance, if we have a point that's like at 2 comma 3, which would be roughly up here, there's no other combination of numbers that will put a point in that same location, right? Like, 4 comma 6 is somewhere else, -1, -2 somewhere. There's no coordinate that is at 2 comma 3 in the rectangular form. But in the polar system, you can have multiple coordinates that are in the same location. And that has some applications later on, but that is a really important thing to emphasize here, is that in the polar system, points are not unique, okay? That means that there's essentially going to be infinitely many points that are in the same location. So there's a couple of examples. Let's look at a few more oddball ones that might be a little trickier. Okay, take a quick look at these three. Notice the big thing that's different with these three is that now we've got some negatives worked in there. So what I'd like for you to do is, and I know that I haven't taught you how to deal with negatives, whether they be on theta or r, but I want you to try to see if you can plot these out yourself. And what I mean by that is, just take out a sheet of paper, sketch out your x and y axes, draw some concentric circles, and just try your best to estimate where this point is going to be. And do it for all three. And then, pause the video, and then once you think you have at least your best guess as far as where they are, I'll show you where they should be and how you handle these negatives, and just to see if, whether or not you're right. Let's check your gut instinct, so to speak. So yeah, take a moment, pause the video, and then unpause it, and we'll go through how to do this. All right, hopefully you had a chance to at least try this out. Let's walk through each one of these. So 4 comma negative 2 pi over 3. So once again, we have, let me throw this up there as well. We've got, can I fit all this on there? I'm going to have to move that over, aren't I? Just a tad. Okay, that looks fine. Okay, so the first thing we want to do is we want to locate theta. Now, in this case, theta is negative. So when you have an angle that's in standard position, positive angle measures rotate counterclockwise, so like 15, 30, 45, and negative angle measures rotate counterclockwise. So this could be like -15, -30, -45, -60, -75, -90, etc. So -2 pi over 3 is going to be down in this third quadrant. One easy sort of shortcut here to figuring out exactly where that angle measure should be is just to reflect the positive angle measure over the x-axis, and that'll give you exactly where it should be. So in other words, if I reflect this terminal side of 2 pi over 3, positive 2 pi over 3, over the x-axis, we see it overlaid with 4 pi over 3. And so that angle measure, really is right here. So that is where -2 pi over 3 is. Let me, let's see here. Let's make this a little bit more obvious. Here we go. So, okay, so that's negative 2 pi over 3. So that is the angle measure for which we are going to move away from the pole. And since the r value is 4, we are going to move 4 units away from the pole. 1, 2, 3, and 4. So our point would be 1, 2, 3, 4 right here. So B is a little different in that the r value is actually negative. So let's talk about how you're going to handle that. So the first thing you're going to do is the same thing as we did before, is you're going to locate theta. And in this case, theta is 7 pi over 6. So I'm going to label that right here. Let's see, where's 7 pi over 6? There we go. And so in this, it's a positive angle measure, so the theta here is this angle right here. But we want to go through that, we want to start from the pole and go out r units. Now if r is negative, we kind of have to rethink how we're going to do that. The one thing that I think works pretty well is once you've identified your angle measure is to label that as like the positive end of a number line. Okay, so like let me just like if this is the positive end of the number line, then the negative end of the number line would be in the opposite direction. So if this is the positive, then if I just draw like a straight line, going through there, looks like my last one wasn't too straight. Let's try to delete that other one. Then that would be the negative direction. So over here is where your negative r value. So now we've got basically a number line here where the positive r values are going this way, negative r values are going this way. So negative 3 comma 7 pi over 6, again you would find 7 pi over 6 and then you realize, oh, I'm going in the negative direction, so I actually want to go away from that angle measure. 1, 2, 3 units, and that would be right here. So, and we'll practice this a little bit more, but just to throw it out there while we're talking about it is, just to reemphasize that points are not unique. There are other coordinates that are in this same location, right? Like we could say that, for instance, 3 comma pi over 6 would be an equivalent point. It's in the same exact location. So we'll do that on the next one as well. Just kind of try to find other points that are in the correct spot. Let's see here. Let's get a pi going. There we go. So there we go. 3 comma pi over 6 is in the exact same location. Let's look at C now. For C, we have a negative 2 as our r value, and our theta value is 4 pi over 3. So first, we want to find theta, which is 4 pi over 3. And since I'm noticing that the r value is negative, instead of just noting where 4 pi over 3 is, I'm also going to continue the line all the way in the negative direction. So in other words, here's my number line where I have 4 pi over 3 as the positive direction, where this would be like if the r value is positive 1, positive 2, positive 3, positive 4. And the negative direction would be in this direction. So this would be like negative 1, negative 2, negative 3. So negative 2, 4 pi over 3. We find 4 pi over 3, which is right here. The negative direction, we're going to count negative 2. 1, 2. So our point here should be right here. Now when you sketch these out, you don't have to draw these lines, but I do find them helpful when we're trying to make sure that we're in the right place. Again, it's not really all you need is the point, but if you're kind of struggling to figure out exactly where it goes, drawing these lines can help. But like if I go ahead and erase them, I can kind of clear up exactly what's happening here. Let's get rid of all this. And so now you can see kind of where everything is. All right. So there's a couple of different examples here of plotting points. Before we move on to the next thing, just real quick, let's find a point that is in the same location as C here. So this is negative 2 comma 4 pi over 3, but we could also call this, let's see here, 1, 2 comma pi over 3. So 2 comma pi over 3, let me just do this real quick, would be a point that is in the exact same location, okay? And we'll go over how to find these a little easier. If you're looking just at a graph, sometimes it's kind of easy to just kind of see where you might find another one. But let's go through how you would actually calculate where other points would be. Again, something I've emphasized a lot here is that polar coordinates are not unique. So we can find multiple different points at the same location. So let's say we wanted to find different polar coordinates that are in the same location as the given one. And oftentimes what I'll ask is, find a polar coordinate that's in the same location as this, but that fits some kind of restriction. So maybe I'll say, find a polar coordinate that's in the same location with a negative r value or a negative theta value. And let me go through and show you how you can find many more points that are in the same location. So one strategy we can use is by adding or subtracting 2 pi. Now, essentially what's happening here is that, let's see, can I write pi? Nope, I'm going to have to do an equation here. Well, what's really happening here is, there we go. Oh, okay. There we go. Let's fit it right up there. What's really happening here is that we are doing one full revolution. So let me just do a quick little sketch here. So let's say, we've got a point that's right here, right? So if this is my angle that the point is on, the terminal side that the point's on, if I rotate one full revolution, and I'll end up back where I started, right? So if I add 2 pi to my angle measure, I'm going to end up exactly where I started. So in this case, let's say we had pi over 12. Let's see here. There we go. So we got pi over 12 plus 2 pi. And we can add that, and I'll show you how to do that. And we also could subtract 2 pi, because remember, if I subtract 2 pi, then I'm going to rotate, but in the clockwise direction. So adding 2 pi is going to rotate the counterclockwise direction, but subtracting 2 pi will rotate in the clockwise direction. So both of these should be able to allow us to compute another point that's in the same location. So just as a little refresher on how you would add these, you need to find a common denominator. So the common denominator here would be 12. And so we need to rewrite 2 pi as something over 12. So let's see here, that'd be 24 pi over 12. See, that's kind of hard to see. Let me pick a different color there. I just wanted to kind of separate these out. Here, let's just go black. Oh, that didn't change a darn thing here. Okay. Bear with me here, y'all. I apologize. Let's see. There we go. Okay. So we can find a common denominator here, and then we can see 1 pi over 12 plus 24 pi over 12 is going to equal 25 pi over 12. So we can do a very similar thing here and subtract 2 pi, and in effect what we're doing is rotating clockwise versus counterclockwise. So let's go ahead and find another common denominator for that one. It's still going to be 24 pi over 12. But let's see, we want to subtract here. So 1 minus 24 would be negative 23. So let's say I asked for a point that's in the same location as 7 comma pi over 12, but with a negative angle measure. this would get that for you. Let's say I asked for one where the angle measures in between 2 pi and 4 pi, then you could give me this one. So depending on what other restriction I give you, you can do either one of these two things to find another theta value for that. So the positive 7 is still going to remain the same. So let's go ahead and write our new point. All right, there you go. So so we've got two coordinates that are in the same location as 7 comma pi over 12. And again, just to restate this, the way we found that is we added or subtracted 2 pi. So that's one technique that you could do. There's something else too. What we could do is, instead of rotating a full 360 degrees or a full 2 pi, we could just rotate half of that. In other words, rotating pi radians or 180 degrees. And when we do that, we'll be kind of in the wrong direction, but we can negate the r value. In other words, if we were to rotate so that we're over here, but we change the r value to be negative, that can kind of push us back where we need to be. So we can do that whether we add pi or subtract pi. So the second thing the second technique we can use besides just adding or subtracting 2 pi is we can negate r, meaning flip the sign of r. If it's positive, we can change it to negative or vice versa. But along with that, we need to either add or subtract 2 pi. Or not 2 pi, I'm sorry, just pi. All right, so let's go ahead and do that with our point. We can negate r and then either add or subtract pi. So to negate r, we're just going to flip this to be -7. So we'll just know that this will be -7 for both of our coordinates. And let's go through the process of adding or subtracting pi instead of 2 pi. So if we want to add or subtract pi, then we, just like we did over here, we're going to need a common denominator. So the common denominator would be 12, and so this fraction should be 12 pi over 12. So 1 pi over 12 plus 12 pi over 12 would be 13 pi over 12. So one coordinate could be -7, comma 13 pi over 12. Similarly, we could subtract pi and do basically the same thing. So let's go ahead and throw that in here. We're going to do subtraction. Let's make this kind of stay consistent here with the coloring. So if we subtract pi, we're going to need to find a common denominator again. It's going to be the same one, so it shouldn't be too much of a surprise here. We got minus 12 pi. So 1 minus 12 would be -11. Okay, so we're doing this to figure out what the new angle measure should be. We're going to also negate r. So when we write our coordinates here, we should have -7, comma 13 pi over 12, and we'll have -7, comma -11 pi over 12. So look at all these different combinations. So if I ask you to find different coordinates, under certain restrictions that are in the same location, each one of these is a little different, right? Like we've got the first one, which has a positive r value and a positive theta value. This one has a positive r value and a negative theta value. Over here, we've got a negative r value and a positive theta value. And down here, we've got a negative and a negative. So, I'll usually ask you something like, find a coordinate that's in the same place as this, where both r and theta are negative, in which case you're probably going to do this. Now, it's not necessarily going to give you exactly what you want. If you follow this, you might have to do this more than once, or it really just kind of depends on what the point is. But this is 4 different things you can do to find different polar coordinates that are in the same location as a given point. So the last thing we're going to go over today is how to convert points from polar form to rectangular form and vice versa. So let's say we have some point, that's just, well, just to keep it simple, we'll put it in the first quadrant here. It's just sort of some generic point. I'm not going to put a number on it. But what we need to do is we need to find a relationship between the variables in polar form and rectangular form. And what I mean by that is we need to come up with some equations that will allow us to calculate, for instance, x if we know r and theta, and y if we know r and theta, if we want to go from polar to rectangular. And if we want to go from rectangular to polar, we need to find equations that will allow us to calculate r given x and y and theta given x and y. So we need to come up with some relationships that exist between these values. So let's really break down those 4 coordinates, x, y, r, and theta. So x represents the horizontal distance from the origin that the point is. Y represents the vertical distance, right? No surprise there. R is going to represent the distance from the pole or the origin. So this distance from here to here is r. That's a pretty ugly r there. Well, I don't know if that made it better or worse. And then anyway, theta is going to be this angle in standard position. So really, there are a few different equations we can come up with that relate these variables, but I think the easiest way to kind of show this is to draw a right triangle and then use the trig functions that we learned in the first unit to help us convert these. So let me draw a little triangle here. Okay, a little right triangle, and we can see that, for instance, x squared plus y squared equals r squared. So I'm going to go ahead and write that as one of our equations. X squared plus y squared equals r squared. So that's one equation that will relate x, y, and r. So if we knew x and y, we could compute r, right? So that's one thing. Now, what else can we see here? Well, what I'm going to do is, just to make this a little bit more obvious, is I'm going to move, I'm going to sort of rewrite this. So I'm going to say that x is this distance right here on the triangle, right? And then y is this length, and then r is over here. Just make it a little bit easier to see there. So in that case, we can use those SOHCAHTOA functions, right? Those right triangle trig ratios. For instance, cosine of theta, which is adjacent over hypotenuse, would be x over r. Sine of theta would be y over r, opposite over hypotenuse. So let me write down those 2 equations as well. So let's see. Cosine of theta, I'm just going to type theta here, I'll go back and fix that in a minute, equals x over r. And similarly, sine of theta equals y over r. Okay, so if we know theta and r, we could compute y using this equation. And if we knew theta and r, we could also compute x by rearranging this equation. So I'm going to put that up here and kind of organize this a little better. Okay, so there's one last thing that we're missing here, right? So if we have x and y, we have an equation that we can use to compute r. If we know r and theta, we have an equation that we can use to compute x and y. But what we're missing is an equation that allows us to compute theta given x and y. So the last equation we are going to use is tangent of theta, and tangent's opposite over adjacent, so in this case that would be y over x. And this is going to be the final conversion equation that we're going to use. Now we're not going to use these as they're written. We're going to rearrange these to make them a little easier to use. So let's do that. I'll do that down here where we rearrange these. So we say like x equals whatever, y equals whatever, et cetera, et cetera. So yeah, let me fix this theta real quick and then we'll do that. All right, much better. Okay, so if we're going to go from polar to rectangular, what that really means is that we are going to take a given r and theta value and we're going to convert it to a rectangular x comma y. So we need to write an equation for x and an equation for y that are in terms of r and theta. So we'll get those equations by rearranging these two functions for cosine and sine. So like if we solve this for x, for instance, what we would do is multiply r on both sides. In fact, let me just go ahead and copy this over here. So if we multiply r on both sides, we would have r times cosine theta equals x, right? Or if we want to really make this a little nicer, say x equals r cosine theta. So if we know r and theta, we can just plug it into this equation. We can compute x. Similarly, we could rearrange this sine equation for y and solve. And if we're given r and theta, we can solve for y. So y equals r times sine theta. So here we go. If you've got r and you've got theta, now we have equations here that you can use to solve for x and y. And it's real simple. You literally just plug in the values that you need. You might need to use your unit circle to compute these trig values. If these thetas are not angles that are on your unit circle, then you would just use a calculator. So these two are our conversion equations for going from polar to rectangular. Now let's say we wanted to go from rectangular to polar. It's kind of the same deal here where we're just going to come up with two equations. There's one little thing that I'll elaborate on, but for the most part, you're doing kind of the same thing here. So instead of going from r comma theta to x comma y, we're going to go from x comma y to r comma theta. So if we're given x and y to compute r and theta, we are going to rearrange these two equations. Now, the top one is going to be a little bit more obvious here. Okay, just take the square root of both sides and you're basically done. So let me go ahead and put that down here. So we want to take the square root of both sides. And when we do that, I'm going to clean this up and put the r over on the left-hand side here just to make it a little bit easier to read. So r is equal to the square root of x squared plus y squared. So if you know x and y, you can just plug this in, you get your r value. Now to find theta, this is really the only tricky part here because when you take to solve for theta in this tangent function, we need to take the inverse tangent of both sides. Okay. Now when we do that, we run into a little bit of an issue because of the domain restriction that exists for the inverse tangent function. And you don't really need to, if you forgot that, it's not a big deal. But just as a little reminder, the restriction for inverse tangent is negative pi over 2 to pi over 2. So this formula is always going to give you an angle measure that's under 90 degrees or it's in between negative 90 and 90. So that poses a little bit of a problem because if your angle measures like in quadrant 2, for instance, that's going to be an angle measure that lies outside of the domain here. So what we have to realize is that this angle measure that this formula is giving us is actually not the theta that we want. This is not going to be the correct theta. It might be, but what this actually is giving us is something called the reference angle. And I know it's been a long time since we talked about reference angles, but the basic idea is if you know the reference angle, you can still figure out what the original angle is. You just have to look and see what quadrant you're in, and depending on what quadrant you're in, you'll do something a little different to compute it. So let me rename this angle theta, and I'm going to rename it theta reference angle. So again, this may or may not be the actual angle that we want. Most likely it's not going to be. In fact, the only time it will be the reference angle is when you're in quadrant 1. So if you really want more information about reference angles, go back to your notes in the first unit, and I elaborate on this quite a bit. So I know it's way back in Unit 1, so I don't want to spend a ton of time going back over reference angles, but I just want to kind of show you how you're going to get the actual theta. So to actually compute theta, you have to look at which quadrant you're in, because this reference angle is only going to give you like an angle that can actually go in a right triangle, or a negative version of that. So to actually get theta here, we're going to split this up into 4 different cases, okay? So depending on if you're in quadrant 1, if you're in quadrant 2, if you're in quadrant 3, or if you're in quadrant 4. So I'm just going to make myself a little bit of room here to write all of these. So over here, I'll show you how to calculate it if you're in quadrant 1. Over here, quadrant 2. And you might, this might ring a little bit of a bell, because what we're going to do is something that we've done before. Back when we talked about inverse trig functions, actually that might have been Unit 3 or 4, somewhere around there. But we had to go through this process before, where we have to identify what quadrant we're in before we can actually find the real angle. So if you're in quadrant 1, then the reference angle will just be theta. So there's not like, you don't have to do any extra calculations here. You'll just see that theta will just equal the reference angle. Okay, so there's, like I said, no computations to do. If you're in quadrant 2, so if you're over here, then the angle measure that you're going to be given, and here, maybe I should kind of sketch this out so you can kind of see what I'm talking about. If you're in quadrant 1, this is your angle measure, and that's theta and the reference angle. When you're in quadrant 2, the reference angle that you're going to get from this equation is this angle right here, but what you really want is this angle right here. So in quadrant 1, they're the same, but in quadrant 2, you really want this one over here. So to compute that theta, you are going to add pi units to the reference angle. Okay. In quadrant 3, and let me do a little sketch here. The reference angle is going to be down here, and the angle you actually want is this one. So as you can see, you're going to have like this angle measure. It's going to be like, let's say it's like 30 degrees or something, and we want to add 180 degrees, which would be the same as adding pi. So whether or not you're in quadrant 2 or quadrant 3, you're actually going to do the same thing. You're going to add pi to your reference angle. And finally, if you're in quadrant 4, then, which would be down here, the reference angle is going to be negative. It's going to give you a negative angle measure here. And what we want is, well, let me stay consistent with the coloring here, else I might throw you off. The actual angle we want is right here. So to compute that, we're going to add 2 pi. So you'll have like a negative, let's say negative pi over 6 or something like that. And then you'll add 2 pi to get the actual angle that you're interested in. So a lot to remember here. I'm not going to ask you to memorize all this. I would just, in your notes, make sure you have these written down somewhere. Let me go ahead and box this out so kind of call out the different ways. So quadrant 1, the angles are the same. Quadrant 2 and quadrant 3, you're going to add pi to find theta. And then in quadrant 4, you're going to add 2 pi. Oh, you can't see that, can you? Let me, let's see, can I pull this over a little bit? Is that going to work? Okay, yeah, there we go. You can kind of see me in the background here. Okay, so there we go. We've got formulas to convert from polar to rectangular and formulas to convert from rectangular to polar. So I have these written down somewhere for easy access. There's just basically an equation for x, an equation for y, and then you have an equation for r, and then this one's kind of the annoying one, the equation for theta, because the only equation we can come up with is going to give us the reference angle rather than the actual angle itself. So we'll have to do like 2 steps here. So let's do a couple of examples here, and then that's going to be it for today. So here's an example where we want to go from polar to rectangular. It says convert the point 2, 2 pi over 3 to rectangular coordinates. Now take a look at this grid. What I've done here is I've overlaid, and it's not perfect, it's a little skewed, but basically I tried to overlay a Cartesian or rectangular grid on top of a polar grid so that you can kind of see and get an idea of what the point should be. So 2, 2 pi over 3, first I'm going to find 2 pi over 3. All right, and that's going to be right here. Here's 2 pi over 3. And so 2, 2 pi over 3 means I'm going to go out 2 units starting from the pole, so 1, 2. Okay, so there's my point. Now, if I were going to ballpark what the rectangular coordinates are, obviously it's going to be it's not intersecting at the grid point, so it's not super obvious, and this grid's not perfect either, but it should be around -1, 2. Maybe not exactly, but around there. So when we get our answer, we're going to kind of expect it's going to be somewhere in that, vicinity. So let's go ahead and convert. What we have here is we have r and we have theta. So this is my r, here's my theta. So if we want to compute x and y, we're just going to use these 2 equations up here. So I'm going to go ahead and copy these. Just, let's see. So, okay. All right, calm down there. Nope. There we go. And then let me copy the other one as well, just so that we don't have to keep scrolling up. Yeah, I'm going to get good at this eventually. All right. So we've got a formula for x and a formula for y. And so all we need to do here is we just need to plug in the values that we know. So we know r is 2, and we know theta is 2 pi over 3. So this is something that you can use your unit circle to evaluate. Let's pull up the unit circle. So we're looking at 2 pi over 3, and we're interested in what cosine of 2 pi over 3 is. So cosine refers to the x coordinate on the unit circle, which is in this case going to be -1/2. So we've got 2 times -1/2, which is going to be actually exactly -1. So my grid is off a little bit there, and I apologize for that. I don't know how. I guess I just need to find someone who's actually done this for real instead of just superimposing 2 images. But so my x value is -1, which is pretty much where I thought it was going to be, right? We said it was going to be in the vicinity of -1, 2, and the fact that it's exactly -1, that's pretty good. That gives me a good degree of confidence I got that right. So let's calculate y. So we need r sine theta instead of r cosine theta. So the theta in this case is going to be 2 pi over 3. The r value is 2. And so we need to compute sine of 2 pi over 3. So let's take a little gander at this unit circle. And it looks like, okay, sine of 2 pi over 3 is going to be √3 over 2. So I'm going to hide that again. √3 over 2. So what we have here is we've got 2 times √3 over 2. So when I multiply 2 times √3 over 2, the 2's are basically going to cancel out. And so I actually just get y equals √3. So it's -1, √3. Now √3, if you throw that in your calculator, you're going to get something like, like 1.7 or so. So the fact that it was, that is kind of a little under 2, that seems like that could be right. So our final answer, if we want to convert 2 pi over 3 to a set of coordinates that is in rectangular form, it would be -1, root 3. So let's say we want to convert -2, 2 to polar coordinates. So let's find -2, 2 is going to be roughly here. Again, it's not going to be perfect. That's okay. We just want to get an idea of approximately where it should be. Now, -2, 2 looks like it's on 3 pi over 4, like exactly. And that would make sense because that's at like 45-degree mark after 90. So we can kind of expect that to be our angle theta, although we will calculate it. And it looks like the R value is going to be in between 2 and 3, although not 100% confident because I don't know that this is gridded perfectly, but we should expect it to be somewhere probably less than 3 for that R value. So to calculate R, we are going to use the equation that we had above. To calculate theta, we're going to do that whole, that's not the right equation. So here is the equation to find the reference angle, and that's just going to give us the reference angle. We have to note which quadrant we're in, and we are in quadrant 2. So what we want to do is, so since we're in quadrant 2, we want to add pi to the reference angle. So we'll compute it, and then we'll add pi. So theta here, in fact, let me just go ahead and pull that equation down, just so that we don't have to keep scrolling back up. There we go. Is going to be the reference angle plus pi. So we'll throw this in the calculator, we'll add pi, and we'll be done. Let's go ahead and compute what this would be. So the R value is going to be square root of x squared plus y squared, which is going to be -2 squared plus 2 squared. And let's see, what would that be? Let's see, so that'd be 4 plus 4 is 8. So we'll just call it root 8, and we'll be done. You can simplify it more than that, but it's really not necessary. So R is going to be root 8, which if you were to put that into your calculator, and I wouldn't necessarily recommend that you do, but if you put root 8, you get about 2.82, which does confirm what we were suspecting, that this R value would be a little bit less than 3. Okay, so that does kind of add up. Okay, so that's my R value. Let's go ahead and calculate theta. So first let's find the reference angle by doing inverse tangent of y over x. Oh, okay. There we go. Well, like I said, one of these days I will figure out this good old program. Let's move this out of the way. It's kind of getting in the way here. Okay, so in this case the y is 2 and the x is -2. So this is just the inverse tangent of 1, and so what that's going to end up giving us is pi over 4. Okay, so if you put that in the calculator, you get the same thing. If you just evaluate that, you will get pi over 4. Now once you have the reference angle, we can find the actual angle pretty easily. We were expecting it to be 3 pi over 4, and that's exactly what we're going to get. Because if we add pi to pi over 4, we need a common denominator there. So the common denominator here would be 4. So instead of writing pi, we're going to write 4 pi over 4. And so we get, oh, wait a minute. Hold up here. Hold up here. I got an issue. We all got a problem here. We got a big problem. The inverse tangent of -1 is not pi over 4. It's negative pi over 4. That's my bad. I'm trying to work too fast and type while I'm talking. It should be negative pi over 4. So really, this should be negative pi over 4 plus 4 pi over 4. And what kind of caught my eye there was that if that wasn't negative, then we would have gotten 5 pi over 4, which is the wrong angle measure. 5 pi over 4 is down here. So I went back and just took another glance, say, okay, well, there's a huge red flag here where the angle's not where I'm expecting it to be. And so let me go back and just check my work and say, okay, oh, wait a minute. Inverse tangent -1 is negative pi over 4. And again, you can verify that in the calculator. So now that I can add these, I am going to end up getting kind of what I expect, which is that theta is 3 pi over 4. So I've located my coordinate. Okay, it's going to be root 8, comma, 3 pi over 4. And that is going to be the coordinate in polar form that is at the same location as -2, comma 2 in rectangular form. So that's it for today. Be careful when you're trying to do that reference angle. That can be a little tricky. Let me know if you'd like me to go into a little bit more detail, and we can talk about that. But that's it for today. Hopefully this polar system, I know it's new and it can be a little tricky at first, but as you work with it and you practice plotting these points and converting from rectangular to polar and vice versa, you are going to get better at it. Let me know if there's anything I can help you with, and that's it for today. Y'all have a great one, and I'll see you next time.